Hey everyone, ready for another deep dive?
Always.
Today, well, you know how some things are like solid and brittle,
Yeah.
like this mug,
Mhm.
and then other things are liquids or gases at room temperature.
Right.
It's kind of wild to think about, right?
It is, yeah.
So, we're going to use our chemistry study guide to figure that out today.
Okay.
We're going to be looking at the world of ions and ionic bonds.
Sounds good.
And I guess before we really get into it, can you remind me what exactly an ion is again?
Sure. An ion is basically an atom, or sometimes even a group of atoms, that has an electrical charge because it's either gained or lost electrons.
Ah, yeah, right. Okay. So then that brings us to like table salt, right?
Yes.
Isn't that like a classic example of ionic bonding?
It is. It's a great example. So you've got sodium, which is a metal,
Mm-hmm.
and it tends to give away electrons.
Okay.
And it has one lonely electron in its outer shell.
Okay.
And then you've got chlorine, which is a nonmetal,
Uh-huh.
and it really wants to gain an electron to fill its outer shell.
So it's like sodium is saying, hey, chlorine, you want this electron.
Exactly. And chlorine is like, yes, please. So sodium loses an electron and becomes positively charged, and chlorine gains that electron
Right.
and becomes negatively charged.
Right.
And then those opposite charges attract each other.
So they stick together.
Exactly. And that's how you get sodium chloride, which is table salt.
Oh, wow. Okay. So it's all about this like giving and taking of electrons leading to this attraction. But how does that affect whether something is a solid or a liquid or a gas?
So remember those dot and cross diagrams from the study guide?
Oh, yeah, vaguely.
Well, they can actually help us visualize this whole thing.
Okay.
Basically, imagine you're drawing the outer electrons of an atom as dots and crosses.
Okay.
And you can see how sodium loses one of its dots to chlorine, which completes its outer shell of 8 crosses.
Okay. I think I'm starting to remember this.
Good. So these oppositely charged ions don't just attract in pairs. They actually form these massive organized structures called lattices.
So wait, it's not just a random jumble of ions.
No, they have an actual structure. Imagine like tiny Lego blocks snapping together in a repeating 3D pattern. That's what an ionic lattice is like.
So it's all very organized.
Yes, very. And that's what gives ionic compounds their high melting points. Because to melt or boil them, you need to break apart those strong bonds holding the lattice together.
Oh, right. I see. So the stronger the bonds, the higher the melting point.
Yes, exactly. But it's not just about the individual bonds. It's also about the types of ions involved. For example, magnesium oxide has magnesium ions with a 2+ charge and oxygen ions with a 2 charge. That creates a much stronger attraction than the 1+ and 1 charges in sodium chloride.
Oh, wow. Okay. So that's why magnesium oxide has a way higher melting point.
Yes, magnesium oxide melts at over 2,800 degrees Celsius,
Wow. That's crazy.
while sodium chloride only melts at 801 degrees.
So that must be why they use magnesium oxide for like high temperature stuff, right?
Exactly, like furnace linings and things.
That's pretty cool. But is it always like super black and white? Purely ionic or not?
Well, not always. Some ionic bonds have a bit more of a covalent character.
What does that mean?
It means that the electrons are shared a bit more than transferred. And this happens because of something called polarization.
Polarization.
Yes, where the electron cloud around an ion can be kind of distorted by the charge of a neighboring ion.
So things get a little more complex.
Right. It's not always so simple. This kind of reminds me of how table salt dissolves in water, but something like sand doesn't.
Huh. Yeah, that's interesting. Is that because of bond strength?
It is, yeah. It has to do with how strong the ionic bonds are within the compound, and also the attraction between the ions and the water molecules.
So it's like a tug of war.
Yeah, you can think of it that way. If the water molecules are strong enough to pull the ions apart, the compound dissolves. But if the ionic bonds are too strong, the water can't break them apart and the compound stays insoluble.
Like sand.
Exactly like sand.
Okay, so we've got these ions all snapped together in their lattice.
Yeah.
But like that makes them sound kind of static. How can they conduct electricity then?
Well, that's where state change comes in.
Okay.
So in solid form, those ions are kind of locked in place.
Uh-huh.
They can't move around, so they can't carry an electrical current.
So like they're stuck in their lattice, unable to move.
Exactly. But when you melt an ionic compound,
What happens?
well, those bonds that are holding everything together, they start to weaken.
Okay.
The ions, they get enough energy to break free
Oh.
and start moving around.
So now they can move.
Yeah, and because they can move, they can carry an electrical current.
Oh.
Each ion has a little positive or negative charge.
Right.
And when you apply like an electrical potential,
Yeah.
Those charged ions start to flow towards the oppositely charged electrode.
Oh, that's cool. So it's like creating a pathway for the charge to flow.
Exactly.
Okay, but what
Exactly.
about dissolving an ionic compound in water?
Ah,
Does
so,
that do the same thing?
it's similar, yeah.
Okay.
When you dissolve an ionic compound in water, the water molecules, they're attracted to those charged ions.
Uh-huh.
Remind me, what are water molecules again?
Well, right. So water molecules, they are polar.
Polar.
Yeah, it means they have a slightly positive end and a slightly negative end.
Huh.
And they can kind of surround the ions and pry them away from that lattice structure.
So the water is pulling the ions apart.
Yes, exactly. And once those ions are free to move around in the solution,
Yeah.
they can carry an electrical current again.
Oh, wow. This is making me think about batteries.
Yes,
Aren't they kind of doing the same thing?
absolutely. Batteries use the movement of ions to store and release energy.
Oh, that's so cool.
Yeah, so inside a battery, you have these two electrodes.
Okay.
And they're separated by an electrolyte, which is basically a material that lets ions flow through.
Mm-hmm.
And when the battery is discharging,
Uh-huh.
chemical reactions release ions, and those ions flow from one electrode to the other, creating an electrical current.
And when you charge a battery, you're making the ions go back where they came from.
Exactly. You're storing the energy for later. So it's all about the movement of these tiny little ions.
It is, yeah. It's amazing how something so small can have such a big impact.
This is blowing my mind. I never realized how much was going on.
Yeah. It's really fascinating.
So, like, what else can these ionic bonds do? Okay, so ionic compounds can conduct electricity when they're melted or dissolved.
Right.
But what else can they do? I mean, they can't all be batteries, right?
Right. Ionic
Hmm.
compounds are actually all around us.
Really?
Yeah, they're not just in batteries or like salt shakers.
Okay.
They're like in the concrete of buildings.
Wow.
Yeah, and ceramics.
So this mug is ionic.
It is.
That's so cool. And what about fertilizer?
Oh, yeah. Fertilizers often use ionic compounds too, like nitrates and phosphates.
Okay.
These compounds dissolve in water
Mm-hmm.
and release nutrients that plants need.
It's like they're feeding the plants with ions.
Pretty much.
So it all comes back to these barns.
Well, it does. It's amazing, isn't it?
Yeah. So, like, I'm guessing the specific use depends on the properties of the compound, right?
Absolutely.
Like you said, they're not building skyscrapers out of table salt.
Haha, no. So the properties like strength and melting point all come from the ions involved
Uh-huh.
and how they're arranged in that lattice structure.
Like ceramics, they're super durable, right?
Exactly. Those strong bonds give them a high resistance to heat.
Oh, okay, I see. It's all about those bonds.
It really is.
Wow, this is incredible. We went from simple table salt all the way to like spacecraft heat shields.
Yeah, and we can't forget fertilizer.
Oh, right, of course.
Yeah.
And it's all thanks to these tiny little ionic bonds.
It's amazing what these little things can do.
Well, this has been an incredible deep dive.
It has.
We've learned so much about ions and ionic bonds.
Yeah, and how they shape the world around us.
So to all our listeners out there,
Yes.
keep exploring, keep questioning, and keep diving deeper into the world around you.
Exactly. There's always more to learn.
And who knows what amazing discoveries you might uncover. Thanks for joining us on the deep dive.